So back to preventive intervention randomized trials. This is a context that I've been part of. I've been part of this prevention science methodology group for some years, a group developing methodology for preventive interventions. Hendrix Brown is the leader of that, University of South Florida. And as a person with trained in statistics, I then have to sit and try to translate this flowery language from developmental epi people. So I've enjoyed trying to translate this and to talk about determining levels and variation in risk and protective factors, as well as developmental path within a defined population in the absence of intervention. This then should be, can we not? Oh, okay. Sounds like I need a new battery. Let's see. Okay, we have technicians coming. Cutting in and out. Looks like this is a line. Think the microphone is hanging too low, or?
No, it sounds good, but let's just replace it just to be safe.
Let's see. How does that sound right now? And if I turn this way, you still hear it? All right. So this is growth modeling with the random effects in the control group in the absence of intervention, and then directing interventions at these risk and protective factors in an effort to change the developmental trajectory simply means S on X. That is, the intervention changes the slope. In evaluating variation in intervention impact across risk levels and context on proximal and distal outcomes. Context means that you have a multi-level modeling situation, students in classroom. Proximal is the actual growth model outcomes. Distal is what we'll look at soon, a later occurring outcome that is influenced by the earlier proximal growth process. So yes, it is possible to translate, and this led to a paper with me and my former postdoc, Pat Curran, in psychological methods, where we worked with the idea of multiple group analysis with a twist, which might be of interest to you. You can read through this yourself. It's a classroom intervention. It's a good behavior game intervention. It's carried out here in Baltimore Public Schools by now by the group that Nick Ailongo is in charge of. It continues, and you measure kids in the fall of the first grade, and then start a good behavior intervention aimed at reducing aggressive, disruptive behavior in the classroom. And you study the development through at least grade 7, and more data is coming in. So the outcome is a TOCA teacher-rated rating of each child's aggressive behavior. It's actually a measurement instrument, but we're just going to use the total score. And the question is if this intervention reduces the slope of the aggression trajectory, and whether or not the intervention is differentially effective for different kinds of kids. And here's a set of analyses that we did. It's a multiple group setting, so we did an analysis of each group separately, and then a two-group analysis, joint two-group analysis in the sense that we talked about, and without interaction. By that, with and without interaction, by that I mean that the key question here, one of the key questions was, is there a treatment baseline interaction? That is, for instance, are kids who are high aggressive in the fall of first grade before the intervention, will they benefit more or less from the intervention? And there are various ways of dealing with that kind of baseline treatment interaction. And then we did various modifications of the model to see if the results were sensitive to alternative model specifications. And then step 6, we did a power analysis, basically trying to figure out could we have gotten away with a smaller sample and still found these treatment effects. So let's go straight to the end of this analysis and then see how we got there. So on your right screen, you have on the x-axis grades 1 through 7. There measures and fall and spring, so there are several time points here. On the y-axis, you have the aggression score, teacher rated for the kids, and the higher it is, the more aggressive the children are rated as. So here we have decided to display the results in terms of 3 groups: high initial aggressive, medium, and low initial aggressive. And each group then, if you look at the top one, for instance, has 2 curves, where the dark curve is, or the light curve rather, is the normative development that takes place in the control group in the absence of intervention. And the dark one is the corresponding development for those who got into the intervention group. They are the same before the intervention starts due to randomization. That's the model specification saying that. And we then want to see how the intervention manages to pull down the aggressive behavior development. So the difference here, say at the end of 7th grade, is a treatment effect. Although you could argue that the treatment effect is really the whole area under the curve, because the longer the kid has been kept non-aggressive, non-disruptive, the more the kid might have learned. So a definition of treatment effect is an interesting question. But more importantly, for children starting lower aggressive, the treatment effect seems to be smaller. And in fact, you have this opposite effect here with that wonderful word, iatrogenic. Oh, I did it. I said it right the first time. Iatrogenic. So here the intervention seems to make kids worse. We don't know if that's real or just statistical non-significance showing up. So the question is, how do we get to this end? What is the modeling that leads to this nice figure? And here's the answer. And this is all in Psych Methods, which is a journal that forces methodological statistical types to write in an understandable way. So it takes forever to get papers through there, and people send them elsewhere. Now, all right, so you have 2 groups again, control group and treatment group, and you notice one feature here. As opposed to males, females, we now have different number of factors, different number of circles for the 2 groups. And this is a way to pinpoint what the intervention does, what the intervention contributes beyond the normative development that would have been if you hadn't been randomized to the intervention. So you reason as follows. You have here a quadratic growth model. Apparently the Q factor is fixed, has 0 variance, because you don't have any covariance involving that. Apparently we have centering at time 1 because S and Q don't influence Y1. And we have some P widths, residual correlations here. That's a normative development. Now you can say in the treatment group, since they're randomly equal to the control group people, you can say that there is a normative development, those 3 growth factors up here, but an extra development due to the treatment, extra development being captured by an extra growth factor T that influences Y2 through Y8. So the idea is to hold every parameter of the normative development, the growth factor parameters here, equal across the 2 groups, whereas the treatment group has an extra development due to treatment. What comes to my mind is sort of a value-added approach. And the advantage then is that you pull out a treatment-specific growth factor. In this case, it's a linear growth part, could be quadratic. And the size of this treatment-induced growth can be a function of I. So there's the treatment baseline interaction sitting down there on that path. Treatment baseline interaction, if I is high, which is the fall of first grade aggressive behavior, then T may be high or low. So usually when you talk about treatment baseline interaction, people say, okay, let's split the baseline Y1 into high, medium, and low and see if the treatment effect is different. Here, instead of splitting the sample and instead of working with an observed Y1 as a baseline representative, we take I, the latent growth factor, to be what represents baseline status. And then have the treatment baseline interaction be this regression. If that was 0, there would be no treatment baseline interaction. There would just be a main effect of T. So that's the general idea of that paper. And if you try to do a regular multiple group analysis with mean differences in the S and Q, you wouldn't get as powerful of a way of pinpointing what the treatment effect is. And we show that alternative in the paper. So here's the input. It's a multiple group analysis, 111 control group children and 75 treatment group children, quadratic growth. And in addition, you have a linear growth part, in which we will only, as it turns out, we will only use that T growth factor in the treatment group. We're going to zero it out in the control group. Now here we go from parameterization, our standard parameterization 1 to our alternative parameterization 2 by fixing the growth factor mean to 0 and instead holding the intercepts of the outcomes equal across time. It's equivalent in terms of model fit to parameterization 1, but it is easier often to have the growth factor mean 0 in terms of interpretation. Here you see some equalities again in the overall part of the two-group analysis, which means that these growth factors, I and S and Q, that representing the normative development, is held equal to the corresponding parameters in the treatment group, since we mentioned them in the overall. And down here is the T on I, which allows for treatment baseline interaction. Let's see, 73 then is model control. So here we have the same equality of S and Q, and then in control we want to get rid of T. So T on I is fixed at 0 and the mean of T is 0. So essentially you can mark here in the margin, for the control group, T is not present. There is no T factor in the control group on the left screen. That's what we do here, the last two statements of the control group. But otherwise, going back one slide, the growth parameters for the first three growth factors, I, S, and Q, are held equal. And it's a reasonably well-fitting model, mostly probably because the sample size is fairly small. So there's an advantage to having a small sample size. You get a better fitting model. You don't have as much power to reject your false notions. But that should not be the driving force for choosing sample size. Here is the key result on slide 76. For the control group, there is no T involved, so T on I is 0. However, for the treatment group, T on I is negative 0.052 and significant. So T on I, negative, significant, what does that imply? Well, it says that the higher I is, the lower T is. As I increases, T goes down. And how do you interpret that in this substantive context? As I goes up means that as the more aggressive the children are in the fall of first grade before treatment, the lower the T, and T is the slope, the linear slope for the post-treatment development. And low slope is good in this case. Lower slope means we go like this. Clock hand goes clockwise. You know, it's not clockwise from my side. So, but anyway, so and as the slope, linear slope here, the treatment-specific linear slope goes down, and it pulls down the aggressive behavior. So it's the negative is good here. It's what we want. In this, well, let me put it this way: the treatment effect is therefore more accentuated. The treatment effect is bigger the higher I is. The higher I is, the more negative the linear slope, which is good. So the treatment effect is bigger the more highly aggressive the kids are. That's significant on slide 78. And if you look at slide 79, the last line of slide 79 gives the intercept of T. If there hadn't been any T on I effect here, then the intercept of T would have been the mean of T, and it would have been the main effect. And if it had been insignificant like T is here, it would say there is no main effect. And in fact, for this study, there is no main effect, which we often find in preventive intervention studies. No main effect, but there are interesting effects for subgroups of individuals. And that's what the T on I captures. It saves the day in a sense. The more highly aggressive kids are the ones who benefit the most. So that model on slide 71 is, when you get the model estimates, you can give the values that go into this model estimated plot. And the fact that there's a bigger difference up here than down here is due to the fact that that coefficient down there is significant. So this is a model that you may want to try out. Let's see what else we want to say about it. Let me just say this. There is a limitation of this model, and that is that the treatment effect is monotonic in the sense that the treatment effect is low or zero, higher, and higher still. This approach could not be used if you had a treatment that was beneficial for children who are average aggressive, but not strong enough for those who are high aggressive, and no effect for those who are low aggressive. So you have the treatment effect in the mid-range of the baseline of aggressive behavior. So if the distance between the curves had been the biggest in the middle and small on both sides of it, this model would not have worked. And what we're using instead now, and what has been used on the Hopkins Baltimore data, published in JCCP, and on our website under growth mixture modeling, is a growth mixture model approach, a mixture model approach. So instead of a multiple group approach, you allow for treatment effects that interact with the baseline, actually treatment effects that interact with different normative trajectory classes. So you imagine that you have, say, without the treatment, you have three different kinds, qualitative different kinds of development. Normative, and well, let's say just two, normative and high aggressive development without intervention. And then you can say the intervention effect is different for the two classes. That is a growth mixture modeling approach, which is more flexible and handles this situation on your right screen as well as the situation where the treatment effect would be biggest in the middle. So there's several papers on the website on that, but that's a topic for November 11 in Ann Arbor. So come to Ann Arbor. Who is the representative of the consulting group Ann Arbor again? All right, over there. Talk to this lady about any details that you want to know about. So, okay, that's rounding off the multiple group approach. Let's now talk about multiple indicators for the remainder until we get to lunch. So we're down here on our list. Why would you talk about embedded growth models too? All right. So let's first try to absorb what this slide 82 says. And they may say more than you want to know, but nevertheless, you have it here. In the beginning of times in Alexandria, people had to scribble all this down. But in any case, so what this represents is 3 time points. Let's start with simple facts. 3 time points. And for each time point, you have a measurement instrument, here represented by only 3 items to fit it on one page. The same 3 items given at each of these 3 time points. Those 3 items are thought of as unidimensional, measuring a factor. You could write F1 here, F2, F3 for the different time points. And the growth model is considered for these factors. That is, the factor variables are the dependent variables, the outcomes, so to speak, for the growth model with an intercept and a slope. So it's a latent outcome variable. Seems like an oxymoron. Latent dependent variable. So here you're really trying to use the details, the detailed information from your measurement instrument. So TOCA, for instance, has 13, 15 items, and actually measures a couple of different dimensions, 2 or 3. This could be one of those dimensions and measured by a subset of the items. In fact, all that we're going to talk about now could be done for multiple factors going forward, multiple factors derived from the same measurement instrument. And in fact, in one of the web talks on 2-level modeling, I do that analysis and show that different dimensions in the TOCA actually have different growth trajectories. Dimensions like verbal aggression, physical aggression, and property-related aggression. Now, since we have a measurement model here, this is a one-factor analysis model. We have the usual factor loadings, lambda, and measurement intercepts, the nus and u parameters. And down here we have the dependent variables with its residuals, and down here we have the growth model with the factor loadings 1, 1, 1, and the time scores 1, 2 for the slope factor, centering at the first time point, now corresponding to F1. What's written here at the top is how the means progress over time, and we don't need to go through that, but for those of you more technically inclined, and I know there's several of you who are, this represents here the mean of this first item at the first time point, and the second item, the third item, and the mean of the first item at the second time point. And nus are the intercepts here. The factor means are start here. The factor mean is fixed at 0 for the intercept factor, which then you know that corresponds to parameterization 2. And I said that yesterday that for categorical outcomes and multiple indicator outcomes we use parameterization 2. Growth factor mean is 0. The intercept for the factor is 0. So the means for the observed variables will be just the intercepts of the measurement equation. Second time point, you add the means of alpha 2 for the slope factor, and multiplied by the loadings. So here you have the progression of this. So there's a very distinct progression of the means of the indicators across time, which may or may not hold true in the data. So we're going to tell you how to approach this analysis to make sure that the items behave in a proper way for growth modeling of a factor. You know, I mentioned the loneliness of twins, our favorite examples, and I feel lonely, although it was supposed to be an analogous item measuring loneliness as nobody loves me. We saw that I feel lonely had a very beautiful cubic development over the lifespan, but nobody loves me was pretty flat. Those two items would not follow this mean structure over time and should not be used together in a multiple indicator growth model. In fact, if you had only two items, you could still do this analysis, but it wouldn't be easy to discover the misfit unless you did, because you only have two items per factor, and you should never have only two items per factor, unless you did an analysis of each process separately, which we did. So this is a complex analysis, and therefore you want to, again, do this very carefully, stepwise. Only after you master all of the other things we talked about these 2 days. Certainly, number one, if it's a new measurement instrument, you always want to start with an exploratory factor analysis of the indicators for each time point. To make sure what the dimensions are, and see if there is truly a single dimension for the items that you hypothesize should have that. Then you determine the shape of the growth curve for each indicator, do the growth modeling for each indicator, and the sum of the indicators can be used too as just a simple down-to-earth proxy for the factor. Summing up these three items will be a proxy for the factor value here, which means that you would do a regular observed variable growth model. That's useful to do, even though it's not exactly what you want to do. It's useful to do to gauge what the growth model should look like. The fit of the growth model for each indicator that should be good, and the growth model shape should be the same. So you can't have one item being a cubic development and the other linear, then the multiple indicator model is rejected right away. You may also want to do a confirmatory factor analysis of all time points together. Confirmatory factor analysis meaning only this part of the model, not adding the growth part, but only this part, which I would call a longitudinal factor analysis model, where if you want to study how the means of the factors change over time, you want to hold the measurement parameters, nus and lambdas, equal across time, fix the factor mean of the first time point to 0, and estimate the means for the other time points as higher or lower than 0 to represent increase or decrease in the factors. So that's a confirmatory factor analysis without the growth model, and then at the end add the growth model with measurement invariance across the time points. So why would you go through all that painful work? Well, there is advantages to doing that instead of just summing up into a proxy using the average. First of all, if you use the average, you don't know if the items are unidimensional, measure the same construct. You would also allow for, when multiple indicators, you essentially allow for using unequal weights in the formation of the factor by having unequal loadings. And importantly, you can allow for partial measurement invariance. It's very often the case that the items work different. The same item functions differently at different time points, different ages of the respondent, for instance. And whereas most of the items work the same across time, some of the items may not, and that could not be handled if you just use an average sum score. But it can be handled in this multiple indicator approach. And another advantage is that you don't confound the time-specific variance and the measurement variance. You know, when we talked about an observed outcome here, on slide 82. This residual has a variance which contains variation due to both time-specific variation and measurement error. You can't separate the two, but when you have multiple indicators, the measurement error sits up here in these residual arrows, and the time-specific variation sits down here, and they are estimable, identified separately. And furthermore, when you use multiple indicators like this, you have the chance of getting smaller standard errors for the growth factor parameters, smaller confidence intervals, because you have a stronger model, if it is true, if it fits well, more restricted model using the item-specific information. Using the item-specific information is therefore definitely worthwhile. So we applied this to the TOCA data for 7 aggression items. That seemed unidimensional, at least at the time. And the model looks like this. Let's see, how many time points do we have? Spring grade 1, spring grade 2, 1, 2, 3, 4 time points. 4 time points. And the picture is a little bit complex, but it shows, you know, here's the factor at the first time point, second time point, up to the 4th time point. And we only drew the indicators for the first and the last time points. So you have, I forget what BRU is. Breaking rules, how can I forget? And fighting and harming others, lying, is stubborn, teaching classmates, yells at others. Yeah, you know these acronyms, don't you? So there's the model, and then we go through a whole sequence of analyses based on topic 2 type of approaches. So first of all, input excerpts here now for Mplus. First we do CFA with no measurement invariance. So CFA, we drop the bottom part of the picture and just do CFA, longitudinal factor analysis, confirmatory factor analysis, and we just measure each factor by the corresponding items at that time point. And there's no equality, no measurement invariance imposed. So we want to compare the fit of this model to a model with factor loading invariance across time. So you see these 1 through 6 at time 1 equal to 1 through 6 at time 2, 3, and 4. So this is factor loading invariance, which seems to more easily hold than the next step, which is factor loading and intercept invariance. So here we bring in not only lambda invariance, but also nu invariance. And that comes, I guess, on the second page here. 91. The nu invariance measurements intercepts are in brackets for the dependent variables. And we're saying, if you look at this construction, for the item breaking rules at first, second, third, and 4th time point, they're all equal to one single parameter nu. So this is nu for breaking rules, and this is nu for fighting, etc. So each of the 1, 2, 3, 4, 5, 6, 7 items at the 1, 2, 3, 4 time points. So all of the nus are held equal in addition to the loadings held equal. And when you do that, when you have the nus, the measurement intercepts equal, you can actually identify factor mean differences across time. But you can't have all the factor means free, because then the model is not identified, and you have an indeterminacy. You can increase the factor mean and decrease the nu, and you get the same fit. You don't need to estimate all the factors. You have a reference point, say the first time point, where you fix the mean of the factor to 0. That does not imply that the observed variable means are 0. As we said, the observed variable means are then the measurement intercept. And all you need to know is whether or not the factor mean at the other time points are higher or lower than 0. It's only the difference that's identified, and that's all that you need. Sometimes people really get upset by the fixing at 0 here, but it's quite logical to do so. So when you have measurement invariance, you can identify the fact for the intercepts, you can identify the factor mean differences across time. So far, we're only doing CFA, no growth modeling. Only doing the top part of the picture. This kind of invariance testing we went through quite a lot in topic 1, mostly across groups. But it's a perfect analogy between multiple group analysis, testing of measurement invariance, and multiple time point. Perfect analogy, same approaches. Here is partial invariance for the intercepts, so slide 93 is a key. We found that from modification indices that not all of these intercepts were invariant. So for instance, you see that we have dropped out some 1, 2, 3, 4 places. So harming others, I felt like saying hollering at others, but it's harming others. At the fourth time point, we don't have invariance anymore. Fourth time point, harming others, mu seems to need to be different than for the first 3 time points. So you get 2 estimates for the intercept for harming others, one for the first 3, which is equal, and then a unique one for the fourth time point. Likewise, for stubborn, it's not invariant across all of 4, nor for TCL, whatever that was. But you know, there's 1, 2, 3, 4 times 1, 2, 3, 4, 5, 6, 7. There are 28 intercepts. Only 1, 2, 3, 4 of the 28 intercepts are non-invariant. And all of the loadings are invariant. So we have largely measurement invariance. A partial invariance is only with respect to the intercepts, and only a few of the intercepts at a few of the time points. So then we have only partial non-invariance and don't have to worry much about it. For in the SEM literature, there's an article by Byrne, Shavelson, and Muthen that talks about that partial invariance matter. Usually referred to as Byrne et al., and I'm the et al. You know, you work hard, but if there are 2 other authors, you get into number 3 and you're just an et al. It became a very popular paper, but I'm et al., you know. But, you know, at least I'm not bitter about it. So this is perfectly fine. We can still say that we have the same factor measured at all the time points, just a little bit of non-invariance. And you have a impressive report here on testing the sequence of models that we talked about. Measurement non-invariance has a chi-square test of fit. Measurement loading invariance has another chi-square. The difference is given here with the difference in number of degrees of freedom here. So the loading invariance seems to fit well. The chi-square is 14 with 18 degrees of freedom. Chi-square is low relative to degrees of freedom, meaning that loading invariance fits well. Loading plus intercept invariance, 73 with 18 degrees of freedom. That doesn't seem to fit well. This is significant. This chi-square value relative to the degrees of freedom is too high, indicating a misfit of full measurement intercept invariance. So let's just have a partial one, freeing those 4 intercepts we talked about. That drops down the chi-square from 73 to 25. Quite a lot better. Still significant, but a lot better. Question is if we have to allow a little bit more non-invariance. But we can stop there. And then adding the linear growth structure at the bottom, namely the I and S influence, governing the mean and covariance structure of the factors. That additional structure is fitting very well. 7.77 chi-squared with 5 degrees of freedom. Very good fit for that extra structure imposed by the growth model. So the crux of the matter is in the measurement invariance, and in my limited experience here with multiple indicator modeling, it seems like loading invariance is easy to find, the intercept invariance less so. And interesting enough, historically, multiple group analysis was only developed for loading invariance testing, not the mean structure measurement intercept testing. And I think a lot of measurement non-invariance didn't get discovered because of that. Which is interesting historically, and bear with me, that in the IRT world, in item response theory world, it's the opposite. There the focus is mostly on the intercepts. Like Roche modeling, you talk about item difficulty, and people focus totally on the item difficulty invariance and non-invariance, less so on the item discrimination, the slope factor loading invariance. So but at least now we come to convergence and know that we should consider both intercepts and slopes, both difficulties and discrimination. And here's an explanation of chi-square differences that you can read on your own, enjoying that. And here is the growth model then finally added. On slide 97, growth model added with time scores applied to the factors. So you have a growth model with factors as the quote-unquote outcomes. That's fine. Mplus does not protest. And that's the model that we're looking at on the right. And the results? You see, for instance, here then the factor. And here are the factor loadings. I'm on slide 98, factor loadings for the 7 items. And here you have the intercepts for the stubborn item across the time points. The first 2 held the same, but the last 2 allowed to be different, as we mentioned. Just output excerpts. To summarize the findings, on the x-axis you have the factor, higher aggressiveness to the right, and on the y-axis you have stubborn, the item, continuous item, it's a Likert scale. And we said that the intercept is different, actually higher for the later grades than the earlier grades. So we do this plot that we did consider a lot in topic 1, and is also considered in IRT, item response theory, item bias or diff, differential item functioning analysis. Stubborn is regressed on F, right? The slope is the loading. The loadings were the same across all 4 grades for this item, but the intercept is different. Intercept different meaning that they are parallel but separated vertically. So like an ANCOVA plot, right? Treatment control plot. But so that's saying then, for instance, if we go in at this factor value here, low aggressiveness behavior, low aggressiveness factor value, in earlier grades with a lower intercept, we would expect a lower stubbornness value for the observed variable than in later grades. So the same factor value makes us expect different stubbornness values. Or put another different way, for a certain stubbornness value, going backwards, for a certain observed stubbornness value, later grades indicate a less severe aggression level for F than if that stubbornness value had been observed for earlier grades. So that's a clear indication of measurement non-invariance, right? When the same observed value really represents 2 different factor values. So, but if you account for it in the modeling, you're okay. You're not distorting your results. Let's talk about this a little bit more in detail, this matter of measurement invariance. It's an interesting case of technology that's available but underutilized. We can consider 4 different cases of degrees of invariance across time. What we have studied is the case where we have the same items at all the different time points. And we started out with a baseline assumption that all items were invariant with respect to lambda and nu. And if they are, we certainly feel comfortable saying that we have the same construct at each of the time points. And we really want to have the same construct at each of the time points because growth modeling requires the same variable in the same metric at the different time points so that you can study change. So that change at the differences across time is really a difference between individual outcome behavior rather than differences due to item behaving differently. We had to switch over to case 2 where, although we still had the same items, some items were non-invariant, at least with respect to some of the parameters. But the degree of non-invariance was fairly small, so we felt comfortable saying that we're measuring the same construct of aggressive behavior. Case 3, we have less invariance across time. We actually have different items, or at least some of the items are different across time. This is the case of LSA actually. You know, we talked about those 60 items. The outcome, the Y's that we work with were actually IRT scores, theta hats in IRT language, based on different sets of items at the different time points. But some items are the same at adjacent time points, enabling you to do an equation operation, so you put the score on the same metric at the different time points. We'll talk about that in a second. You can handle partially different items across time, where some items are invariant and still claim that you're working with the same construct which is necessary for growth modeling. And then the most complex case is case 4, where you have different, at least partially different items, and some items invariant, but there's too little invariance to the point that you really can't be sure. You probably do have different constructs over time. And actually, in LSA, you could argue that if you start with grade 7 and go up to grade 12, grade 7 has items mostly containing numbers and operations, and then grade 8 you sprinkle in algebra and geometry, and then calculus in later grades. So the item content shifts and over grades, and you may argue that you don't measure the same construct anymore. I don't know how serious that is, at least not if you're comparing males and females where the item change in content is the same. That's an open question, I guess. But let's look at these different cases with the help of an example here. Simplified example, 4 time points, 3 items. You have the news, the measurement intercept here, and the lambdas, the loadings. First loading fixed at 1 for setting the metric of the factor. Now, this is item A, item B, item C. At the second time point, we find that item C is no longer age appropriate, and we change item C to item D. But we keep item A and B. They are good measures of the construct at both time point 1 and time point 2. We can therefore hold equal the intercept nu A and nu B, whereas we have separate intercept for item C and item D. And same thing for the loadings. So what I'm starting to say is that there is a possibility to change items across time if you do that in a well-designed fashion. This is LSA style, educational achievement testing style, where you have overlap of a majority of items, here represented by 2 out of 3 for simplicity. Overlap of a large set of items, same items at adjacent time points. But you can allow for age appropriate or inappropriateness by switching out items and in new items. So going from second to third, item B is outdated and is replaced by item E. But item A and D are used again. So we can equate the parameters for A and D across time points 2 and 3. And then likewise for the last time point. That's an underutilized approach for in psychology, I think. Certainly it could have been used with TOCA, so aggressive disruptive behavior in grade 1 could have been defined differently, partially differently, than in grade 7. And I think you can think of many applications where you would want to modify your measurement instrument. It becomes much more sensitive to change if you have age-appropriate items. So just by way of saying, this has design influence, influencing designs of future studies, I think, where you can actually, once you know that this is possible, you can think of a measurement instrument design for longitudinal studies where the items, based on substantive theory, could be different across time, but with enough overlap to make sure that we can put the factors in the same metric, which we do by the invariance of the measurement instrument, and argue that it is the same construct across time. So we often have the problem illustrated by the bottom here, often have the problem of having a measurement instrument that's been used for years in a long longitudinal study. And you just use the average of the items, for instance, or the sum of the items. But then new research says this is not a great measurement instrument. We really should change it, or at least change some items. But we can't do that because then we don't have comparability across time for this long time series that we collected. So we're in a dilemma. We want to change it, but we don't feel we can. Well, this idea at the top here could then be drawn on, shown at the bottom. So you say that you start out with the measurement instrument, old instrument called A. Then, time point 2, you can bring in instrument B and give both instruments. So here it's not an item, but it represents several items, for instance. Or it could be the total score. So let's say that's a total score of sum of all the items. Sum of all the items in the old instrument. B is sum of all the items in the new instrument. So time point 2, you give both the old and the new instrument. And same at time point 3. But then by time point 4, you are ready to switch over to the new instrument only. How does this work? Well, this works actually because at least for some time points, do you have multiple indicators? And that is sufficient to identify this factor model here, where you can hold measurement parameters for A equal across these time points, and A across these as well. B measurement parameters equal to here and here, which means that even the single indicator case, which usually single indicators usually can't define or identify a factor, becomes identifiable because you hold its parameters equal to a time point where you have two indicators. So this structure in principle is identifiable. And I try to get people to study it over the years, both methodologically and practically, to see how many time points should we measure both instruments? Would it be sufficient with one, or do you want to have two, or do you need three? How does this work out statistically and practically? But it's an idea, I think, that should be implemented in psychological research, for instance. Both of these ideas. Certainly the top idea of changing measurement instruments is really a powerful one. And I think people don't dare to do it because they don't know how to analyze the data. But now you know that it's very easy to analyze the data, well, if you have the notes. So that then brings us to embedded growth models. So do you recognize this picture? So, you know, with just looking at it for 5 seconds, you know where all of the random effects sit, and then you know all about it. Tells a very rich story, right? You clearly see that intricate interaction between home resources and math courses. Just as a pedagogical reminder here, because as home resources increases, the slope for the time-varying covariates increase, and therefore the effect of math course taking is more powerful on the math achievement. So we really have an interaction here specified as a random slope phenomenon. Exciting, right? All right, let's make it more exciting. So this may not be all that you're interested in when you do growth modeling. How about saying that even the STVC is influenced not only by observed covariates, but by the starting point, the initial status of the growth. The more able you are in the beginning of the time series, the more or the less you will benefit from math course taking. So that's an interaction between I and math course taking, right? You see it? So as I changes, as I increases, STVC increases, and when STVC increases, math course taking has more of an effect on the math achievement. It's an interaction between I and the time-varying covariate. By one word statements, just saying STVC on I, you have a whole new exciting world. And you can bring in true factors, psychometric factors back here. Grade 7 parental and peer academic push. There is a measurement instrument in LSAPE that measures a factor, and the factor is influenced by demographic variables here, and in turn influences the growth parameters, the growth factors, including the STVC. You know, so having a true psychometric factor as one of the covariates, but it's really not a true covariate, it's a mediator. It mediates the home background in its influence on INS. So you have a mediational perspective going on here. Very easy to formulate in the latent variable framework. You just say F by these items, and F on these covariates, and I, S, and STVC on F, and add that to the growth model. This is what I mean by an embedded growth model. So the growth model is only a small part or a part of the total modeling picture that you want to consider. So this framework makes it easy to make these extensions, and the other frameworks can't do it simply. Or, what about this? What does that picture tell you? Except that it's hard to draw. Well, here we're turning math course taking away from being a time-varying covariate to being a set of dependent variables. Why are we doing that? Well, if you look at this picture, take 15 seconds to try to figure out which substantive question it corresponds to, if any. Do you remember how we started off? I think 15 seconds went by. Started off yesterday, we're talking about males and females. Females were doing better than males early on, and then males overtook them, and we wondered if it had to do with males taking more advanced math classes in higher grades than females. Well, then you can ask if gender has an effect on math course taking. But that's not the real interesting question. We want to ask the question, do females tend to take fewer advanced math courses than males, conditional on the male and female having the same math ability? You know, the conditional question is much more interested in the marginal question. That conditional thing is what we just showed for stubborn. Conditional on the factor, it's the IRT diff bias question. So, not only do we let female influence these variables, but we control for I. For two students with the same initial status of math achievement, that tends to influence the course taking they take. do we have a difference in gender effect? So the partial effect of gender controlling for I might be of educational interest. So then I has an interesting influence on math here. It has a direct influence and an indirect influence through the time varying, the former time varying covariates, down and up. And this actually works. I started working with this model, and so far, this far, I could actually do it. I didn't find any effect actually of gender bias controlling for I with respect to this math course taking situation, but I didn't go very seriously. So this is yet another one. And then finally, let's bring in the distal using the developmental epidemiological terms. The distal being high school dropping out. So bringing in more variables into this model, embedding the growth model in bigger context. This is a dichotomous variable dropping out by grade 12, very carefully measured in LSAFE. Dichotomous variable adding to the continuous dependent variables that we have earlier in the model. And dropout then, what should it be influenced by? Certainly by the time invariant covariates. This is then a logistic regression coefficients. But a dropout could also be a function of the growth factors I and S. If you are on a low trajectory, you may be more likely to drop out because a low trajectory of math achievement may indicate a disengagement from school for a challenging subject doing poorly in that, and therefore give you a higher likelihood, higher probability of dropping out. So that's a distal outcome, very easy then to specify. You just say in the variable command, you say dropout, categorical equals dropout, and then you specify the growth model and the f by, and these guys down here become dependent variable, math course on background variables and on I, and then you just simply say the logistic regression, you just say drop out on female mother's education home resources, drop out on IS. So it is almost too easy to say it, but this would be an example of an embedded growth model. Here's another one, which is a little bit too complex to even talk about. This is mother's drinking and head circumference of baby. This is the head circumference at the bottom here. You have a growth model, 3 growth factors for that growth model. You relate that to you control for gender and ethnicity, but you also want to control for mother's drinking. But it turns out the mother's drinking before and during pregnancy has several measurement points and its own growth model for mother's drinking, so can be formulated. So a covariate that is time varying can be given before the growth process starts, time varying before the growth process starts can be given a growth model. And you can predict, instead from an observed alcohol consumption variable, which may be fraught with error, you can predict from the growth process itself. That's a general idea that I tried to be conveying here. I'm not going to get into it because it takes too long. And there's the setup. Let's instead say a few words about power for growth models. There's a lot of writing on power in the literature. This Muthen and Curran psych methods paper, by the way, consisted of a section on power estimation, and he used a so-called Satora-Saris method, which is described in the paper, and we have setups for it here in your handout. An alternative is to use Monte Carlo simulations to estimate power, And Linda and I did a paper on that in 2002 in the SEM journal. You have the reference later on. And it is on the website as well for you to print out. There's a power calculation website connection with this prevention science methodology group that I mentioned. And if you have some interest in randomized prevention studies where you have methodology questions, you can email me, and maybe you want to make a guest appearance talking in our weekly conference calls on that. Multi-level power, multi-level growth modeling being a case of multi-level studies has been described by Miyazaki and Raudenbusch and by all of these people. School-based studies, principles for designing randomized preventive trials, Brown and Liao, Journal of Community Psychology, discusses that, benefits of randomizing on the group level or on individual level. One can consider power for multiple sequential cohort studies, and designs for follow-up. So a lot to be learned in the power area. Just to remind you, power, at the bottom here, it's probability of rejecting a model that's incorrect. We want to reject models that are incorrect, and that's power. Accepting a model that's incorrect is type 2 error. Accepting a model that's incorrect is type 2 error. Type 1 error is rejecting a model that's correct. So if you have a model that's correct and generated data, 100 data sets from that model, you would tend to reject it 5% of the time just because of the variation in this case, chi-square test. Anyway, if you're interested in the power, the Sartorius method is focused on the power to detect that the parameter value is different from 0. It's focused on individual parameter values. There is also writing on power to reject a model, overall model test of fit, by Bob McCallum and others, but that's not what I'm talking about here. This is a series of steps for a power estimation using Sartorius. I'm not going to go through them because you have them here. Again, discussed in the Muthen current Psych Methods article, and the input given in utter detail here, using a little power algorithm in SAS at the end. So these pages will help you in doing it if you're interested in it after reading Muthen and current. It gives you these pretty pictures here, which are in the Psych Methods article, where you have power ranging from 0 to 1. We know we want power of at least 0.8. So the probability of rejecting a model that's false, or rejecting that a parameter value is different from 0, is should be at least 0.8. And it's a function here of sample size, and you can draw different power curves for different kinds of models here, and see for a given model here, for instance, for this model, you need a sample to be above 0.8. You need a sample size of at least 300 or something like that. So you can go through and enjoy these power curves. That's, again, the Sartorius method. And then our paper uses a Monte Carlo study to estimate power. And this procedure is included in the Mplus program and described with several examples in the Chapter 11 of the User's Guide. Chapter 11 of the User's Guide has several examples. So if you're in a hurry for your next grant proposals, and you have a growth model or even a growth mixture model, instead of just walking down to a gym down the hall and having fake power study, you could just, I'm sorry if anybody's named Jim here, you could just copy an example in the User's Guide instead, and you probably get closer to the truth. But with easy modifications of settings in there. So this paper is, since Linda is the first author, is pedagogically written. So it could be understood. And here are the here's an example of what you will find in chapter 11 of the user's guide. You generate data according to a Monte Carlo command. Whoops. You have a population parameter values. You can even add on a missingness structure, attrition across time with a specific structure. And you can then analyze those data either by a model that is exactly right or a misspecified model to study misspecification. But if you want to study power, you want to use a model that's right. And this model is copied from the population model, so this is the analysis model. And then you generate, as it said here, 2 slides earlier, you consider a sample of 500, and you generate 500 such data sets of size 500, and summarize the results from those different replications. So here's what the results look like. We can slow it down a little bit and look at these results. So you have a parameter that you might be interested in, S, the slope on 2 covariates. X2 is a covariate that is binary. It could be your this could be your treatment control dummy variable. In the first column is the population, the true value, 0.25 is the true effect. Second column is the estimate that we get over the different replications. The average estimate is almost 0.25, so we can estimate that well. It tells you the estimation quality. If we had a smaller sample size, the estimate may not have been so close. So you can see what sample size you need to get close to that true value. And then you have the variation, the standard deviation of the parameter estimates across the replications, which should agree with the average of the estimated standard error. So these two values should agree. This is the average of the standard errors that Mplus prints. It should be very close to the true variability, which is taken to be the empirical variation of the parameter estimates across the replications. Summarizing that, the closeness for the parameter estimate, the closeness for the standard error is the so-called 95% coverage, the second to the last column in the Mplus output. 95% coverage means that you have a confidence interval, and the confidence intervals should cover the true value, and it should cover the true value at least 95% of the replications for it to be a good confidence interval. And here you get pretty close. 0.938 is close enough to the 0.95 that you're after. And then finally, in the last column, percent significant coefficient, that 0.83 is the estimate of the power. You want to write, this is the estimate of the power that you have to reject the false notion that X2 has no effect on S. And I'll say that slowly again. Maybe I should have written it down there. Next time. The 0.83 is the estimated power to reject the notion or hypothesis that the influence of X2 on S is 0, when in reality it is 0.25. So if X2 is the, I'll shut up for 2 seconds. It's hard. Keep going. So 0.83 is the estimated power to reject the hypothesis that X2 has 0 effect on S, when in reality it is 0.25. So if this is the treatment dummy, you certainly want to reject that it has no effect on the trajectory. You want to reject it. So you're happy that that 0.83 is greater than 0.8. If you had a higher sample size, it will be higher. If you had a lower sample size, it will be lower. So you can get a notion of how high of a sample size you need to get over 0.80 here. It's a function of sample size, and it's a function of what the true value is. The higher the true value, the easier it is to detect it, the smaller the sample you need. So this is a very practical way of getting estimated power, approximately. The weakness is, of course, you have to make up these population parameter values. For instance, building on a previous study, or general notions of how these people develop. But that's probably better than just going down to Jim, who doesn't know your study at all. It's better that you speculate, and instead of him looking it up in a book that he goes by rules of thumb that are way off. So anyway, study chapter 11. I think you can make headway with it. And even when you have a real data analysis, you can go and say, okay, let me generate data with the estimated parameter values. It's not totally kosher statistically, but it is giving you a notion. If you generated data with the estimated parameter values, how well would you recover those parameter values? How good would the estimates and standard errors be? What sample size do you really need? So it could be that your sample size from which you got those parameter estimates, if you use that sample size in the Monte Carlo study, you have a really hard time recovering the values, which means that your estimates were really fluky, which means they won't be replicated by the next researcher, which means that your paper is in jeopardy of being criticized down the line. So particularly for new kinds of models, two-part mixture models, you may want to do that kind of exercise to not get you into situations where your studies won't be replicated. Yeah, you may want to contemplate this page later. This puts us in a good position for the afternoon, folks, where we start with analysis of missing data. So if we take 15 minutes here now, we can be 15 minutes ahead, which we're going to sorely need when we get into missing data matters. So let's take question and answers for 15 minutes.
My question is 101.
101.
In studies of children and adolescents, quite often in early childhood, responses are based on mother's report. But as the children get older, responses are based on the child's report. So it becomes mother report versus self-report. It could be the same items across all these 6, 7 time periods. Can you treat them as the same, or can you make things equal to account for that, for the different reporters?
So the question is about measurement items that change over time, not only in terms of, not so much in terms of content, but in terms of the actual reporter, child or mother, child early on and then the mother, or mother early and then the child. Well, I would say that you can use this idea then. So early on, it's all mother, A, B, C are mother, and the second time point, at least this item can be reported by the child, and then E and D can be reported by the child, and then all of them can be reported by the child. But there should be some time points where some items are rated by the child, some by the mother, to make this approach work. Yeah, at least one time period where they're both, at least part of them both are measured, yeah. Yes, Dr. Dudley.
Differences you have.
Yeah, well, I think, so if you had a two-group analysis, males, females, you would repeat this model below and do a two-group analysis where you may have hopefully you have some partial measurement invariance across gender for a given time period, as well as invariance for each gender across time. Yeah. Tabby.
Growth model have two groups. Like for example, in a 3-arm clinical trial, can you do it with 3 groups?
So the question is, can you do more than two groups in the multiple group analysis? Yes, definitely. There's no extra problem with that. So it just makes it a little bit more complex to do. Yes, in back.
Slide 100.
What?
100.
100.
Yeah, 100. Could you give us some reference papers or books on case 3 specifically? Do you have any good articles on?
Different items, some items invariant, same construct.
Yes.
Reference for that? Well, that's really lacking a little bit. I would say the best reference for that comes from the IRT world, item response theory world. So topic 2 talked about IRT in March. So if you go on the website and look at the references under IRT, the handouts for the March course is on the website of Mplus. You will find references to books by, say, Hamilton and Swaminathan and Baker and others. So a good IRT text if you're interested. But that's more, well, and Steve Rees and Susan Embritson have written a more applied book as well. So applied and statistical books, I guess, do exist. But it's mostly focused on IRT, that is categorical items, but the ideas are exactly the same. But this really literature, applied literature missing here with, say, continuous items in psychological applications. Although, you know, I don't read all of the psychology journals, certainly, so I don't know what's out there, truly.
Slide 104.
Slide 104.
I'm just wondering if you can add another latent variable that represents the slope of the time frame cover it. And I think you might have mentioned this yesterday, where you can test whether the slopes of the time frame covariates vary over time, and how would you add that?
Yeah, okay, so the question is about the slope for the time varying covariates, and the question is, can you have a slope for the time varying covariate that varies across time? Yes. If you treat it as a fixed slope, that is a slope that doesn't vary across people, you would just say map 7 or map course 7, map 8 or map course 8, which would define 2 different slopes. And yesterday we also talked about the possibility of a random slope being different across time. So the slope varies across person and time, which is using the bar statement, STVC 7, STVC 8, etc.
Slope for the time frame cover to the time, so 1, 2, 3, 4. Do you need to do that as well?
No, this one is not defined it's not defined by the I and S bar statement. It's just a separate random slope statement. So it's STVC bar math on math core statement. Yes.
108, please.
108.
This is a question about the digital outcome and the logistic regression there. When you specify dropouts and I and S, does this mean that I and S are this is conditional upon the effect, say, of female on the intercept or the slope, or do you have to specify it again in the syntax?
The effect of I on dropout is a condition on these. Yes, in the sense that dropout is influenced by several predictors, I and female, mother's education, etc. So it's a partial regression coefficient. That comes out by the fact that you say dropout on I, dropout on female, etc. But I'm not sure that was your question.
If you specify in the syntax dropout on I and S, then the effects of female on I, the effects of female on I are included in the model, aren't they? They're taken account of.
Right.
Right.
So if dropout is not influenced by female directly, female has an indirect effect on dropout via I, which is then formulated by the fact that we've already said I on female.
Okay,
Yeah.
thanks.
Right. So it is certainly saying that dropout is influenced by female, even if you don't have a direct effect, because of its indirect effect. Yes, in the back.
On slide 101,
101. This is the time where that computer goes to sleep. We'll let it sleep over lunch and it will be fine afterwards. Okay.
you were saying that you could use the bottom model to develop new measures and test to see whether it's the same as the old one.
Right.
Would that take into account even if the measure is designed to measure changes over time? Is that what the growth model does?
And this is a measurement instrument that measures the status at this time point. And so is B, although a new instrument. So it's the status of the person at that time point. And then the growth model explains the change for that person in status across the time. So the measure, the observed measure is not a measure of change, per se. Is that your question?
Not exactly. I was just thinking if that was a continuous outcome, and it's going to change over time across those measurements.
So A1 changes to A2.
Yeah.
Yeah.
And then you start measuring with B also at the second time point. Would you still be able to tell whether or not A and B are equivalent, or is that maturation from time point gonna confound that?
No, you can certainly tell if A and B are equivalent measures. If this model fits, it says that they are measures of the same indicator. The measurement parameters would be different because they are probably on different scales because of the new instrument. But the fact that A1 changes, A1 scores change for people that A scores change for people between time point 1 and time point 2, that's not validate by using a separate measure at time 2.
Isn't that why you need A2 in there? Because if it isn't there and you have A1 at one and then B2 at the next, you don't know if any difference there is because of maturation or because of different measurement. So isn't it having the A2 and the B2 together that is addressing the concern that you have? Does that make sense?
Sure.
I mean, why is it we have to have A2 and B2 at the same time point, and we can't, as someone over here had wanted to do, have a different...
The major reason is that you want to be able to put this variable in a comparable metric. You want to have the same metric of this over time, and the fact that you have two indicators makes you able to identify a factor. The factor is the same as that factor, and you can define that factor at time 1 even though you only have one outcome, due to the fact that you can hold the measurement parameters equal across time. So the measurement is the same, functions the same for A, time 1 and time 2, but the people change in the scores for A, and therefore you can measure a factor score difference between the two functions. All right, more questions? Yes?
Slide 78, please.
78.
I'm looking at the last two columns. Maybe you have covered this in March. So under standardized and standardized YX columns, some of them are -1, some of them are 0 and 1 and 999. So what do they mean here?
Okay, so the question is about slide 78 and the last two columns, which by the way in version 5 appear separately, not as the last two columns. They are standardizations of the raw estimate in the first column. STD standardizes latent variables to unit variance. STD-YX also adds a standardization with respect to the observed variables. So you sometimes have a 0 you mentioned, and that's because of the original raw coefficient is 0. and the standardization of the raw coefficient multiplied or divided by standard deviations. 999 implies that we cannot standardize, and that's because the variance is fixed here to 0 for Q. So since it doesn't have any variance, you can't standardize for this vector. So 999 either means missing or means it can't be done. Yes, in the back. Oh, we'll get that.
Sorry.
All right, more questions, yes.
On page 82.
Page 82.
Yesterday we learned that with the data set with only 3 time points, it has limited degree of freedom. But would you recommend this model if you have multiple indicators, but there's only like 3 time points?
So the question is, would I recommend this kind of modeling activity if you only have 3 time points? That's the question, right? Yes, certainly. It's 3 time points is not the optimal number of time points, but it can be done. I guess maybe your question is, do you have more freedom to detect model misspecification with 3 time points than if you'd had only a single indicator at each of the 3 time points? So is that the question? Should we make that the question? It's part of the question. I have to think about that. Okay, what were the problems with 3 time points? We didn't have enough degrees of freedom to correlate residuals across time. That would correspond to these guys being correlated across time. You can certainly correlate these measurement errors across time. Another thing was we needed to free these things here. Can we free? You know, we still can't. That's a good question. You still have only 3 outcome variables, you know. So if you look at this part of the model, you can't squeeze out more parameters from this part of the model than if these were observed. I don't think, at least. That would be my tentative first answer. And unfortunately, it's recorded as well, so you can check it later on if it's right. Yes?
Growth model, and you fit it, and it fits well. And then you want to add a whole bunch of extensions. You want to add covariates, you want to add another parallel growth model process or whatever. Do you go back and check the fit of the original growth model to see if it's been altered and set out of whack or something because of other stuff that you do, or you just assume that the original growth model fits well?
So you start with a growth model without covariates, for instance?
Yeah.
And then you add covariates?
Right. And then you add maybe other parallel growth model process, and then you relate the the covariates to each other, or you relate them, you look at interactions, or you look at a distal outcome. How can you assume that, like, the original growth model, you just kind of...
Yeah, right.
Does this make sense?
Yeah, so I guess the general question is, if you have a big model, you start building the model and modifying it, and you have a well-fitting big model, could it be the case that some part of the model that you started with has been altered a little bit to be misfitting now? So even if this expansive model fits well,
Right.
I can imagine that you can still, if you focus on the small part of the model, then it could be misfitting.
I'm just wondering how many checks we should do
Yeah.
as we're building our models.
Well, just going from unconditional to conditional model with covariates, you don't have to do any checks because you haven't altered the specification of the original model. It's the same. You just added to it. But I can imagine that there are other contexts where you would alter the original model, and even though you have a good fit for the big new model, expanded model, you may overlook that there is misfit in the details of marginal models, just because some part of the model fits so well that it hides ill-fitting in some parts. But it's probably pretty rare, I would say. And that's the most I can say in generality.